Okay, guys. So I'm just gonna make a few videos. Probably gonna be more than one to go over complete, all of electrochemistry. I'm gonna assume that you guys haven't learned anything about it. Even though I know you guys have gone over oxidation reduction, but I'm gonna assume that you haven't. So what I'm gonna do is I'm just gonna go way back to the beginning of electrochemistry and then just keep going through and make. I'm not sure how many videos we'll need, but I'll see. I'll just keep making them as we need them. So the first thing that we have to go over is the oxidation reduction reactions. This is the easy money for the AP exam because it's not the crazy cell part. It's just understanding how redox reactions work, which is part of electrochem. Because all electrochemistry reactions are going to be redox reactions. We're not going to see acids and bases reactions anymore. We're not going to see precipitate reactions. We're not going to see gas form reactions. None of that. It's going to be all electrochem reactions, right? So the first thing that we need to be good at is oxidation reduction. And this is probably going to be a refresher on that real quick. So for example, if I presented an equation that looked something like this, almost there. Okay, now if I presented an equation like this, they can easily ask you 4 very easy questions here. Which species is oxidized or reduced? Or which species is the oxidizing agent or the reducing agent? Right? So in order to do this, you have to make sure you're good with oxidation, assigning oxidation numbers, right? Well, remember there are about a few rules, right? I think like 7-ish rules, remember, of assigning oxidation numbers, and let's just go over them real quick. So rule number 1 is that any element in its natural state will have an oxidation number equal to 0. So that means, like, for example, oxygen is normally a gas and is usually written as O2. So O2 would have gas would have an oxidation number of 0, right? And other things like that. The other rule is that for any monoatomic ions, the oxidation number is the charge number. So for example, if you have, I don't know, if you have Li plus, for example, well, that's a mono, one atom, and it's an ion. So the oxidation number for this species is going to be +1, just the charge, right? And remember that for any compound, I guess, with multiple elements, each element gets an oxidation number. The sum of the oxidation numbers must equal the net charge of the molecule. And if the molecule is neutral, well, then all of them have to add up to be neutral. Okay. Also, a good reminder is oxygen is pretty much -2 all the time, unless it is hydrogen peroxide, which looks like this, right? Then the O is going to be -1, right? The oxidation number. Also, H is pretty much +1 most of the time. And usually, group 1, 2 halogens, the oxidation number is the charge. And what I mean by that is that if you have a compound that contains, like, for example, like HF, well, hydrogen is usually +1, and fluorine is part of the halogen group, and halogens usually have a charge of -1. So the oxidation number here, H would be +1, and then F would be -1. And notice that when we add them, we end up getting 0 because this is a neutral compound, right? In any case, so looking back at this guy that we had up here, looking back at that guy, okay, we can assign oxidation numbers here, right? Well, if we use our rules, well, copper has an oxidation number of 0 because it's in its natural state here. Over here, it's a monoatomic ion, so it's +2. Over here, silver is +1. That's the atomic charge, so it's going to be +1. We don't care about the number in the front. Oops, +1. And then here, we have solid silver in its natural state, so that's 0, right? So now, we should be able to tell which one's being oxidized and reduced. Remember, Leo, Ger, right? This means that losing electrons means oxidation, and then gaining electrons means reduction. Now in this case, the copper went from 0 to +2. So since it became more positive, it means that it lost electrons because it became more positive. So therefore, copper solid is being oxidized. And then if you look at the silver went from +1 to 0. It's becoming more negative, so it gained electrons, or gains electrons. And this means that the silver plus aqueous is being reduced. Notice that I'm using the reactants, and that's for a reason. We have to use the reactants, right? Also, let's say if we were to ask about the reducing agents, remember it's just flip-flopped. So whatever's being oxidized is your reducing agent. And then whatever's being reduced is going to be your oxidizing agent. All right, if you're being bored right now, that's good. That means you're ahead of the class, right? That's fine. Let's talk about balancing oxidation numbers, or oxidation reactions, right? After this, we're going to start the new stuff. I know you guys have learned how to balance, but I want to go over it just once, just to make sure we're all on the same page. Balancing in acidic conditions. So, for example, if you have a reaction that's such as this, so we have this vanadium compound mixing with the zinc solid. Now, I'm not going to do it here, but if you want to practice, you can also practice to see, like, to determine which one's going to be oxidized here, which one's going to be reduced. And if you're interested, the zinc is the one that's being oxidized, and then the vanadium here is the one that's being reduced. But you can check it out yourself, but that's the answer. So you should be able to see it. All right, anywho, going back to how to balance this, right? Well, the first thing that you have to do is you have to set up your half reactions, right? So we're going to break this into half reactions. So just make sure that you know which ones to put where, right? Just usually which element it's combined to, that one just goes along with its own element on both sides, right? So like if you have the V there, then you're going to have a V here as well. Same idea. Okay. And then if you have zinc over there, then you're going to have zinc over here as well. Okay, so now the thing is, there's two things that you have to balance always. The mass and then the charge, okay? So the first thing that you're going to balance is the mass. Well, the first equation, I see one vanadium there and I see one vanadium there. But I see two oxygens there and two oxygens there. Now, I can't just do this. Or, 1 second. I can't just do that because now I have two vanadiums and that won't work, right? And I can't just do this either. Just adding an oxygen like that doesn't work. We can't just add oxygen like that, right? So what I have to do is to balance the oxygens, you always add water, right? So since I need one more oxygen, I'm going to add one water molecule to this side, right? Now we have two oxygens on both sides. But at the same time, I've now introduced two H's over here, so I need to balance that. So to balance that, I just add two H pluses over here. Now all the masses are balanced, but we also have to balance the charges, right? So if you look, one proton, one H plus gets you a +1, but we have two of them, so this guy gives us a +2 charge. And this molecule, we have one molecule, and the whole molecule has a +1 charge. So the total charge on this side is, for example, +3, right? On this side, we have a +2 charge from this molecule. We only have one of them, right? There's only a 1 up here, so there's only one of them. And the water is neutral, so it doesn't present any charge. We need these charges to be the same, right? And the only way we can balance them, the only way we're allowed to, is by adding electrons. So we're going to add electrons to the side with the greater charge. In this case, we're going to add one electron, because that one negative will now make this into a +2, right? Okay, same thing down here. Notice that the charges are the same. I'm sorry, the masses are the same, so there's no need to balance. It's all good. No need for water, no need for H+, except there's this +2 here and there's a 0 there, so we have to look at just the charge, right? So to balance the charge, we're going to have to place two electrons here, right? That's an E. Because now they're both going to have 0, 0 charge on both sides. The next thing we have to do is we have to add these reactions together, right? But before we do that, we have to make sure we have the same amount of electrons on both the top and bottom equation. And we don't, because we have one electron here in the first and then two electrons on the bottom. So what we can do is we can multiply the first equation by 2. But if we multiply the electrons, then we have to multiply everything by 2. 2, 2, 2, right? Eventually, these electrons are going to cancel once we add these two equations. We end up getting 4H plus 2 VO2 plus. I'm ignoring the states of matter just because I don't want to write them. I'm just being lazy. Don't be lazy yourself. And then 2 VO2 plus 2 waters. Okay. Plus zinc 2 plus aqueous. Okay, if you can decipher that, that's pretty much all the ones that are over here, right? So that would be your final answer in acidic conditions. Now the question is, well, what if they asked you in basic conditions? Well, if they ask you in basic conditions, you have two options, okay? But I think there's an easy way and there's a hard way. So like, let's say, for example, if they, instead of saying acidic conditions, they said to balance this in basic conditions. Well, basic conditions, you can either learn this whole new way to balance it, or you can just add like 2 steps to your acidic answer, right? So now basic is going to be in red. So basically I have, so I have this equation here in acidic, right, in red. So to make it basic, all I do is I see there's 4 H pluses, so I'm going to add 4 OH minuses to both sides. These are going to create 4 water molecules on the left. So they're going to turn into 4 water molecules. But I have 2 water molecules over there, so I need to make sure that I balance it so I can take 2 away from both. So this is going to turn into 2 water molecules here. The 2 vanadium is still there. The zinc is still there. The 2 VO is still there. The water is now gone, but we have this zinc plus, and we have these 4 OH minuses here. All right, that's really messy, but that's the 4 OH minus there, right? And that would be your answer in basic solution. So acidic, follow the process. Basic, add these 2 steps, add as many OHs as you have H pluses, and then make sure to balance the waters, okay? Alright, that's it for this video, and then we're just going to go over the cell in the next video in detail. Okay.